Rana, with Rupesh Mukund. And I've spent most of my career in animation, working at DreamWorks, at Pixar, essentially building worlds like this. This is from Finding Nemo. It's an underwater reef. It's a dynamic world, so it's not just an image, right? This is a world, you have your school of fishes, and the whole action takes place in this world. So these are obviously very evolved worlds, but they're for storytelling. My co-founder spent most of his career in sites like this. He worked for Caterpillar. He's a robotics engineer, and he spent most of his time building these very complex. These machines are literally the size of a 3-floor house, and he used to build autonomous versions of these. So, I'm sure you know about self-driving cars, but imagine a 3-floor house moving around autonomously at a mine. So that's what he did for most of his career. And we basically met up and sort of, he asked me a very innocent question. His name is Mike. He's like, can we use these worlds that you guys built for storytelling? Can we actually use them to train and test our robots? And that sort of started a journey for us, which is now 5+ years, starting Duality. And our focus, again, very much is how do we take the tools and techniques from entertainment, from gaming specifically, and apply them to solving these kind of engineering, robotics, AI problems, right? So this is just sort of where we come from in terms of Duality. In my talk today, I'm going to basically cover 4 things. I'm going to start with the motivation. Like, why would you want to do this? Why should one even think about using game engines or synthetic data to train AI models? What's the motivation? From there, we'll talk about this concept called sim to real gap. So this is where it starts to get challenging. Once you get the basic idea, then we'll talk a little bit about what's the challenge, what are the difficulties involved. Then, to make this very concrete, we'll take an example, an end-to-end example, simple example of how you can train a vision model using the techniques we are talking about. And then finally, I want to leave you with some resources. So if some of you are interested in actually doing this yourself, or this seems like an interesting area for you, then I want to leave you with some resources that would allow you to do this yourself. So that's sort of the overall goal for our time together today. So let's start with the motivation. So since we are just coming back from lunch, I just thought this was funny, right? Because AI is like super, super data hungry, right? The more data you can give it, it just wants more and more, right? And so this is one of the reasons why you need to start looking at all kinds of sources of data. It's not enough to just get data from the real world. You need to look at synthetic data. You need to get data from wherever you can. And of course, for a lot of the early models, for models like ChatGPT and some of the image diffusers like Stable Diffusion, they learned from internet data. Over many decades, we had collected, as humanity, we had collectively collected a lot of data in the internet. At this point, they've pretty much sucked up all that data. And now they want more, right? That was not enough. And I'll give these slides in blue, the ones that really try to kind of cover some of the key concepts. So synthetic data is essentially a form of artificial data, if you will, that can be used to both train AI models as well as validate them as well, test and validate them. So the other motivation really comes from robotics. So these are just from recently. This is, I think, from maybe two or 3 weeks back. Stanford opened a robotics research innovation center. And you can see that these robots are starting to actually do really sophisticated things. I mean, obviously, driving on a road is pretty cool, but the number of tasks that autonomous robots are starting to take on, everything from making your bed to, I guess, trying to feed you spaghetti. But now notice this third example here where, the lady's trying to hand the robot a box, and the robot's really struggling. Now think about it. A 2-year-old kid, by the time they're 2, they figure out, you try to hand them something, they know how to grab it, right? And then never let go if it's a toy. But the robot's really struggling with that, right? And, the key sort of insight there is that while a lot of the AI models are doing fairly amazing things right now, they've been trained on internet data. It's like, think about somebody learning about life from reading books. You get a good sense of it, but you're not really going to understand unless you live it, right? And so what we are missing is data from the physical world. And this type of data is going to become more and more important to building the kind of autonomous systems. And, it's also known as embodied AI. So, the data sets, that big plate of food that we saw in the first slide, data sets are critical to AI or internet AI. But these kind of simulations and world models are going to be critical to embodied AI and robotics. So this is the other kind of reason to really start to bring in the kind of game engines and the work that we're talking about. And then the third is that it's a more practical problem, right? Like basically, there's a lot of challenges when it comes to collecting data in the real world. It's slow, it's expensive, it takes a lot of time. You have to annotate it. It's not enough to just collect the data. Then you have to tell the AI what the data is, which is called annotation. And again, a lot of that annotation work gets done actually here in India and other places. But the fact is, you're talking about millions of images, and in some cases videos, and then you're talking about like annotating individual pixels. It's pretty complicated, right? There are privacy concerns, and in some cases it's just not possible. Like if I wanted to collect data to build a base on Mars, which is something that NASA and other people are starting to think about. If I want to build an AI model, or I want to build a system that can operate in this environment, I simply don't have access to it. I cannot do it. It doesn't exist, right? So how am I going to create data for an AI system or a robotic system to be on this planet? Let's get a little bit more specific, right? So fine, okay, you're like, fine, you showed me all these reasons for making synthetic data, but why use a game engine? Why not write a program? Why not do it in some other way? Well, I just want to cover a few key aspects that every game engine has, right? I mean, it knows how to basically deal with 3D objects and scenes. It has physics. It has rendering. It has basically certain key aspects, right? It's got a game loop, right? So it's essentially a game loop is basically nothing but a simulator. You're running the same environment over and over again and seeing what changes. That's a simulation, right? So it's got a game loop. So it's got a bunch of things that if I now reframe it in terms of the AI side of things, right? We can have digital twins. So instead of just having 3D objects, if you can have accurate representation of real-world objects, that's the same thing as our 3D objects. Scenarios, that are based on real conditions. So instead of just having levels, if you have scenarios that actually create conditions that exist in the world, accurate simulation, right? Virtual sensors. I mean, those are the things, right? Just like a player looks at your game through a virtual camera, that's a sensor. That's a form of a sensor, right? So you want sensors, and then finally you need physics, but it's a little different. You need physics that's actually deterministic, that works like it works in the real world. So it's a little bit different. Like a lot of times, you cheat with physics in a game. You make it more fun, or you make it more responsive. If you're trying to do this kind of work, you need physics that's actually more grounded, that's actually more accurate. All right, so actually that's a perfect segue to the next area we wanted to cover, which is the sim-to-real gap, right? Or what's sim-to-real. So this is a very key point, right? That the value of synthetic data is essentially how good is it at predicting what would happen in the real world. So let's say I take a ball, I drop it on the floor, it bounces 4 times and then maybe stops. Or maybe it actually keeps bouncing and then goes down the stairs. So that's 2 very different outcomes, right? Now, if I do the same thing, if I drop a ball in my simulation from the same height, is it actually going to match what the ball did in the real world, or is it actually going to do, maybe it just bounces off the walls or does something completely crazy, right? For the synthetic data to have value, it needs to be predictive of what would happen in the real world. If it can't do that, then it could be very interesting, could be very engaging, but it's not useful to train an AI model, okay? So to think about it, to frame it slightly differently, games are judged by how engaging they are, how fun are they to play, right? We have to judge simulations essentially by how good are they at predicting the real world, right? And that's a pretty key difference, right? And that a lot of the work we've done over the last 5 years is really taking technology that is built for making engaging, fun experiences that are, but not necessarily correct or accurate, and turning them into, simulations that are actually accurate. This is an example of actually what sim to real. So this is the level of testing. So over the last several years, we've been very rigorous in our testing. So this is some work we did in partnership with a robotics company in Portugal, where we are actually giving a natural language instruction to an autonomous drone, right? So in this case, the drone is being asked to fly around a tower. So the mission, or what's called the policy of the robot's being written by an LLM. I think it's ChatGPT in this case. But then the test, you can see on the left is the simulation from Falcon. And on the right, we then send that same program to a real drone in the real world to actually verify, right, that the two will match. It's very important to, when you're doing this kind of work, it's very important to make sure that you're doing these kind of tests to verify that things actually match between the simulation and the real world. We introduced one concept here, which I think is also important, called digital twins. So digital twins are basically nothing but a virtual counterpart of a physical object. It could be a room. This room, we could make a digital twin of this room. We could make a digital twin of me, or of the speaker, anything, right? So we can make digital twins of real-world objects and environments, or people or systems. And the reason we use digital twins rather than just, say, 3D models is that they're the perfect building blocks. Remember, we want accurate results from our simulation. So if we start with accurate objects, then it's like, and we have good physics, then we'll get accurate simulations. So that's why we always start with digital twins rather than just vanilla 3D objects, because they're a little bit more representative of the real world, right? They're much better building blocks for us. So this is an example of some digital twins from retail, from a retail customer we work with, right? And you can see that the difference between, let's say, a model for a game, there's clearly not stylization here, but they are very, very realistic models. You can certainly build them, and we have an awesome asset team here in India that does some amazing work. But then you can also scan them, right? So on the left, you see a rig we built so that we can do this very, very quickly over like thousands of digital twins for retail type of applications. In our sort of world, we think about 3 types of twins. We think about environment twins, which is, again, this room would be an environment twin. We think about item twins. So anything in this room, these tables could be item twins, these speakers could be item twins. And then finally, we think about system twins. Those are like the most complicated in a way. So they could be people, they could be self-driving cars, they could be that drone that was flying around. So the system twins actually have fairly complex behaviors, right? So the 3 types of twins that we think about. This is a small point I'll make before getting off of this sim to real thing. Basically, the ultimate simulation is reality itself, right? Reality is 100% correct all the time, whether you like it or not. So any simulation is, in some ways, a form of simplification, right? There's a reason we run a simulation rather than doing it in the real world, because it's easier, cheaper, etc. So there's always some corners you're cutting. And I think what's important is to understand that the corners that you will cut in in how you simulate, will they affect the predictive value of your data? And you always want to minimize that. So that's always the goal. All right, let's make some of these ideas that we've been talking about a little bit more concrete, right? So I'm going to talk about a vision example from beginning to end. We'll take a very scientific approach. We'll start by talking about what is the problem that we're going to try to solve, what will be our process to solve that problem, what tools will we use in order to do it, and then finally, of course, what kind of results will we get from doing this, right? So vision systems are one of the, it's a very common class of AI models, right? So they basically, you can put a camera in the world and you can detect essentially what is there. So you might use them in an automated checkout system at a store. You might use them in manufacturing to look for defects or when something is not working correctly. You might use them on self-driving cars. To basically figure out what's happening around them and then make decisions about how to drive. So these are all examples of vision systems. And there's many different kind of tasks that vision systems can do as well. You can ask it, you can give it an image and say, hey, is there a cat in this picture, right? And it'll tell you yes or no. You can ask it, hey, tell me which pixels represent a cat versus grass. And it's called segmentation. You can do object detection, so you can say, hey, not just that I want to know if there's a cat, can you tell me where in the picture the cat is, right? So it'll actually give you the bounds of the cat. You can ask for depth information, pose estimation. So these are all different kind of tasks you can do with a vision AI model. For our example today, we'll focus on object detection, right? So we'll say, hey, I want to know if there's an object in this image, and can you tell me where that object is? So the process, so this will look maybe somewhat familiar to people who work on games or even animation or visual effects. You generally start by building assets, right? So that first block we have on the left is about acquiring digital twins, right? So you might build them, you might model them, you might scan them, you might have actually CAD models of them. And certainly from marketplaces, you can get assets, you can kit bash them. So there's a number of different ways that you might actually get those 3D models to begin with, just like you would in a game, right? And then, you add shading, you add physics, other behaviors. You might have programmatic behaviors. So in a game, you might write a blueprint or visual coding, or you might actually write C++ code or whatever. You'll attach some behavior to the different actors within your game. So in the same way, for our digital twin simulation, we are going to basically add behaviors to our twins. The next piece is really where the game engine comes in. So we're going to so I'll use, again, game development language. We're going to take these digital twins / assets we've acquired. We're going to assemble them into levels. In our vocabulary, we call them scenarios. Right? So we're going to create scenarios that represent different initial conditions in the real world. So in our ball example, it's like, okay, I'm standing here, the ball is positioned at the right height. That's the initial condition. That's my level to start the simulation. And then, of course, I'm going to run the simulation itself, which is effectively, I'm going to play the game. Right? In this case, I'm not playing the game to have fun. I'm playing the game or running the simulation to create data. Right? Once that data is generated, then we use more conventional AI tools. We'll use AI frameworks, existing foundational models, AI models, to basically train them with that synthetic data that we've generated. And then what we do is we see how good our model is. And we see how good our model is. So remember that sim to real that we talked about? We'll see how good our model is in the real world. Even though we trained it on synthetic data, we want to see how well does it perform in the real world. And based on how we do, we can then iterate and create new data or create more data to make that model better and better, right? So this, we'll talk about the tool here. So this is Duality's Falcon simulator, which might not be starting the play. Oh, let me see. Hopefully this will, oh, there we go. Okay. So this is built, I'll talk over the video. It's built on top of Unreal Engine. So we actually, we are a partner with Epic Games, and we distribute Falcon ourselves, but it's using the Unreal Engine almost like a 3D operating system. And it covers all the concepts we've talked about, right? Like we instead of using projects and new assets or other types of entities that might exist in a game development scenario, here we use digital twins. We assemble them into scenarios, and then you can run that scenarios to generate data, and you'll have all these sensors that will produce the data. So we've taken essentially Unreal, which is made more for game development, and we've turned it into a digital twin simulation platform that's really meant more for robotics engineers, for AI engineers to use, right? So, but it's really the same. It's really the same engine that you're using, but just in a very, very different way, right? And again, a lot of this will look familiar to you, but the vocabulary is different, right? What you call the tasks is different, right? And of course, we've tried to make certain things easier to do. Some things are different, like sensors. You know, in a game engine, you mainly have cameras, which are called electro-optical sensors. You don't typically have other types of like GPS sensors or LiDARs or infrared sensors. So we then, you know, we've basically got our own fork of the engine, and we've implemented other types of sensors as well, you know. So you can see again, classic Unreal Editor here. You know, we've got the outliner. But in the outliner now, you have digital twins, right? And then notice, like, nobody had fun playing the game, but then what you get out of it is data. You can see on the left here a live preview of the data set, and now I've produced the whole data set that I can use for training purposes, right? So very similar workflow, very similar tools, but a very different application, right? All right, I'll keep moving forward. There's a catalog. We also allow users to share digital twins with each other and the data and so on. But I'll keep moving forward. I also wanted to talk a little bit about our AI student, if you will, right? Who is learning here? In this example, we are using a model called YOLO, which is a pretty popular vision model. And the task, of course, you know, YOLO can do different vision tasks. In this case, as I mentioned before, we are focusing on object detection. And more specifically, YOLO is a foundational model, so it already knows how to detect a cat or a dog, a lot of things that you might run across on the internet, but it doesn't necessarily know how to detect a box of Cheerios or, you know, a swag for, you know, for IGDC. So what we are doing in this case is called fine-tuning. We are taking a student who already knows certain things about detecting objects and fine-tuning them, making them learn further about detecting specific objects. So that's actually what we are doing. One thing to keep in mind is training models is like watching paint dry. It takes a long time. You know, there's a lot of iterations that it runs through. The good part is it doesn't need humans to be involved, but it does take a fair amount of compute to train models. The next, we're going to talk about the results, but I want to introduce a couple of concepts here before we talk about results. So when you talk about AI models, especially vision models, there's a couple of things you're looking for. One is precision. Precision is how often, you know, if you give that AI model an image, you know, a model that you've already trained and you give it an image, how often does it get it right versus wrong? So that's called precision. We want to know about recall. Recall is like if I give it, again, an image that has, let's say, a Cheerio box in it, how often does it actually detect the Cheerio box and how often does it miss it? So that's called recall. And it's like our memory. How often is, you know, you're like, oh, I remember this. How often are you right? And then how often do you recall something correctly, right? So, and then finally, confidence is basically how sure is the model in its assessment, right? Is it very confident? It's not so confident. So here are some images to make this concrete, right? So the image on the left, you can see that it's, you know, it found that drawer. It's funny sometimes when it makes mistakes. You're like, come on, that's not a box of Cheerios. But because it's sort of rectangular, it's like, oh, I think that's a box of Cheerios, right? In the case of the right image on the top, it didn't find the Cheerios. I mean, it's probably because the perspective is kind of wonky, right? It didn't think that was a box of Cheerios. And then the bottom image is what we want, right? You were like, yep, I found the Cheerios. I have a really nice, tight bounding box around it. And I'm very sure that that's a box of Cheerios, right? So this is the kind of result that we are looking for. Now, what we did on a single image, you can do statistically across a whole data set. So if you look at the top two graphs on the right here, there's a graph that's showing you precision, right? And you can see what happens is when our AI student, you know, when that YOLO model starts, it's actually not very precise, okay? It doesn't know Cheerio boxes from, I don't know, box of any other cereal or whatever. But then as it iterates, as it learns on its own, it gets better and better, right? Till eventually it sort of plateaus. So it's like us, right? If you like say you take an exam, The first time you take the exam, like especially for chartered accountancy, I believe it's a horrendous exam, right? You take it the first time, everyone fails. Then you take it again, and next time you do a little better, and then you do a little bit better, till eventually you pass it. Now, if you kept taking it, even after you passed it, you'd probably get a little bit better over time, but then eventually, your scores would not change very much. So that's typically what happens when an AI model trains, is eventually it sort of plateaus out, and at that point you stop training the model, right? So this is how you measure how good or bad a model is, right? Did you close that sim to real gap, right? If I obviously train a model on real data, I expect very good results. If I train it on synthetic data, do I get similar results, right? That's when I know I've closed that sim to real gap. And so here's some example with this, with the same work that we've done, right? You can see that the image on the left is the synthetic image on which we did the training. So this is an AI model that was trained entirely on synthetic data. And the image on the right is obviously from the real world, where we are verifying that that model is working correctly, right? And you can see that it's actually doing a pretty good job. So now, does that mean this model is perfect? Absolutely not, right? So there's all kinds of ways you can break this model, right? So let's say if you added, so here, what we did in our initial training is we gave it a lot of different poses. We dropped that Cheerios box into, in different poses on the floor, on the table, whatever. And we created a bunch of images and a bunch of training data from that. Now, what if I suddenly threw in a whole bunch of other objects? Like, you're not going to have the Cheerios box by itself. You might have, a carton of milk sitting next to it. You might have some other box sitting next to it. Now, can our vision model actually tell apart the difference? You saw how it was even confusing that our cabinet with the Cheerios. Now, if I put a Cheerios next to, I don't know, like another cereal box, can it tell them apart? I mean, that's when the model gets better and better, right? And so the important thing is, like, if you remember that workflow chart, we see how well the model does, and then we repeat the cycle. So the more robust you want a model to be, the more accurate you want a model to be, you need to keep creating more and more data to actually make it better and better. I think this is something that Rupesh asked me to just cover as well, is like, what are some other, I mean, we used YOLO, but there's a whole bunch of different vision AI models out there that do different things. Clip, SAM, WIT. And you can use these in many different ways. So this is where creativity comes in. I don't agree that AI doesn't have creativity. You can, the way you put, the way you use AI, the way you combine it with other techniques, you can be very, very creative. So we actually took some of these models. I think we specifically took Dino and Clip and a few other models to do something like this, where here we are inside a virtual environment, right? This is obviously the Unreal character. And you can ask it questions, right? You can say, hey, generate bounding boxes for trees. So in real time, it's basically figuring out where the trees are. This is a technique called visual QA or VQA. So we are running VQA inside the game engine loop, to actually test out how good our VQA system is. Here it's telling you the pixels that make up the trees. But then it gets actually more interesting. How many trees are there? Like, you can actually ask it. So remember that, how we are talking about the difference between internet data and knowing about the world. Here, I can actually ask it questions about the world to see, hey, does it understand my physical world or not? So it actually figures out that, because I've got a puddle on the sidewalk, right, that it actually must have rained recently. So you can start to test things like this, right? And imagine, like, if you wanted to deploy a model like this, an intelligent model in the physical world, you'd have to do a lot of testing to make sure it behaves correctly, behaves predictably, doesn't do surprising things. So here you could do that literally inside a game engine, right? Inside an interactive experience, you can try these things out. This is using a model called Dino, combined with Clip, as I mentioned, ChatGPT. So it's using a combination of models to do something called visual QA. All right, we are doing really well on time. Awesome. Hopefully I'm not going too fast. Let's talk about resources. What if you want to do this? Actually, you have everything you need to do this. If you know Unity, you know Unreal, you know how to use a game engine, you can do this yourself, actually, right? So the first resource I want to talk about is So we are actually releasing, so Falcon currently is only available, it's actually quite expensive, and is only available to enterprise customers. We work with people like the US Army and JPL and DARPA and people like that, right, Honeywell. But next week, we're going to release Falcon non-commercial, like a learning license, Falcon EDU, that will be for students, typically for people who want to actually learn. And my product team was kind enough to basically give you a 3-month free, which is like about a 5,000 rupee value. So just write down the code and go sign up, right? And this is for you guys to come. Thank you so much for coming and spending your time in the session. But this will allow you that vision example that I showed you today, about how to build a vision model to train on detecting Cheerios. You'll be able to do that yourself from start to finish and learn all of these concepts that we've been talking about, digital twins, YOLO, how to train an AI model. You'll learn all of those concepts step by step as you go. So it's not just that we're providing the software, we are providing a whole learning track with it that you can actually use to learn. What we found is there's a huge demand. Like, we're working with a bunch of companies, and most of them don't know. They don't have people who come from the game development side, but they very much need this kind of data. So there's a massive opportunity here. And we feel there's a way for us to help in that by, helping people learn, more people learn how to do this, right? For more on the game development side or open world, kind of metaverse type things, I also teach actually at the California College of the Arts. I've been teaching a class on metaverse design or building interactive worlds for about 3 years, 4 years, since 2021 now. So a former colleague of mine from Pixar, Neil, and I have written we've written the book. Now it's in editorial, which is its own process. But it's a book that very systematically talks about building interactive worlds, very, multiplayer, large multiplayer environments. We start with very basic concepts about how, what is it, what is even a interactive world or interactive experiential world. And then we move to more advanced concepts like how, what kind of economies can you have there? How do you use generative AI within those kind of worlds? So that is being published by BPB and will come out next spring, sometime around April-ish timeframe. So watch out for that. That actually does it for me, but I'll leave that QR code up if anybody wants to sign up for Falcon. So. And that's going to be free. It's free for 3 months, which should be more than enough for you to go through the learning track. Yeah, so I'm mostly interested in helping more people get into this rather than anything else. So, yeah. That's about it for me. I think we have time for questions. I'm happy to take questions, at least a few questions. Yeah. Mukund, do you want to moderate the questions? How do you want to do it? Hi.
Yeah. So I was able to ask about what kind of domain adaptation techniques you use to basically use this synthetic data, work on a physical world, because synthetic data is synthetic data and the real data is completely different. When you speak about IR or infrared or night vision kind of training, which happens with autonomous driving ADAS. Mm-hmm. So what kind of domain adaptation kind of things you follow, or like how you handle BIOS? Basically.
Yeah, no, great question. So I'd encourage you to also go to, on the Duality side, we have a bunch of blogs as well. As we've been working on this, we've also been blogging about what we learned. We are pretty open and transparent. So we have something called a 3I framework. I'd encourage you to check it out. But, our thesis around, so there are different people who have different theories around this. Our thesis is that you want to try and make your synthetic data as interchangeable with the real world data as possible, because you never know what your model is going to pick up on, right? So what we try to do, so in the case of LiDAR or night vision, for example, we actually look at what does real world data from night vision look like, and then are we able to actually replicate that? I mean, to the point, like in the drone example, we'll actually do side-by-side comparisons to make sure that we've got our model right, basically, our simulation model right. So hope that answers the question. Yeah. There should be more. There should be stuff on the site. I mean, there's only so much I could put in the presentation, but you should be able to find more stuff on the site. Yeah, sure. Good question.
Hey, so I wanted to ask that you, in the end-to-end workflow, you said that you iterate over the results and over again by checking it with the real-world scenarios, results. So what if we want to do the simulations on worlds that are not easily accessible?
Not existing. Mm-hmm.
Yeah, Mars. You said in an example that if you want to create a colony on Mars. So how do we go about that?
That's tricky. That's definitely trickier. So if you don't have the real world as a baseline, it gets trickier. So there we sort of rely a bit more on the laws of physics, so thermodynamics, or in rendering, light transport. So you're trying to rely on laws of physics and making sure that your model is following those laws correctly. But I will say that it does, in reality, you have a lot of nuances that come up to things that you had not anticipated. And those things are a little harder to find, when you don't have real-world data to compare against. So I would say that it tends to be, we call it ground truth. So you'll get good ground truth data, but it may not necessarily be exactly representative of what you might run into. Ultimately, when you do create that environment or you do find that real-world data, you may have some gaps there potentially. Yeah. But in a situation where it's like no data or somewhat clean data, I mean, the somewhat clean data is still preferable. Right. So thank you.
One last question, guys.
Yeah.
Who wants to go for it? Okay, cool.
So the end result that you want to do is reduce like real world simulations, or real world test cases, and use these AI or more game engine created works, right? So in that case, you should be able to correlate your let's say images with the real world images.
Yeah.
So let's say that's the realism of this image. How would you go about quantifying that? What does how do you compare these things?
Yeah, so we tend to compare it essentially through the model training, right? So you train a model. For example, if I were to train a model on real-world data, so YOLO, let's take the YOLO example since we looked at it. If I were to train YOLO on images of Cheerios just from the real world, I would get a certain precision and recall out of that model. Now, if I train it on the synthetic data, I will get a certain precision and recall out of that model. So what we do is we compare those very key metrics that you can tell about a model, and that's how we evaluate, right? And what we found is that generally, so in this example, of course, I'm using only synthetic data, but it's a simple example. In more complex vision examples, what we find is that if you combine real data and synthetic data, you get some of the best results. So if you only use real data, you often lack enough data and enough domain variation to be able to get a really good result. If you use only synthetic data, you tend to miss certain nuances that you get in the real world images. And what we found is actually when you combine the two together, you tend to get the best results, right?
So with what you mentioned, that is only possible when you're replicating the real world conditions in with the game engine data, but with game engine data, we are able to do more than what you can do in the real world. So in that case, you are not able to get that comparison. So I think there needs to be something where you can compare both the images and see that if there's a certain amount of realism to that game engine data, right?
So the game engine data actually lets you have more variations, if I understand your question correctly, right? So, for example, one of the things we'll do is in the synthetic data, the one that we are producing from Falcon, we'll do a lot of variations on lighting conditions.
Yeah, lighting.
Typically, it's very hard to do in the real world, like actually resetting up lighting or waiting all day long for the lighting to change. Yeah, so these are all forms of domain variation, right? So you want to try and do as many variations as you can across your domain of operation, basically, right? And so your test data, in this case, I'm assuming your test data has a nice representation also across the domain of operation, right? So even if I don't have, let's say, golden hour lighting for my real data, or I don't have afternoon lighting, as long as I have it within my synthetic data, and then I have an example of that in my test data, I want to see how that performs, basically, right? Okay. Yeah. Okay. Awesome.
Thank you so much, Apurva. I'm sorry, I have to cut this